Okay. Okay, so we're almost done. 1.5 hours more to go. Well, actually less than that. 75 more minutes to go. Okay, so well, you can start your mental countdown, and in the meantime, let's talk about infinity, countable, uncountable, and then uncomputability. Okay, so that's what we'll talk about today. Oh my God, yeah, it's working. Okay, all right. So today, what we'll talk about, what we'll start talking about is questions like this. So, well, we have the natural numbers, we have the integers, we have the rational numbers, the real numbers, the complex numbers, etc. So how many of each are there? There are infinitely many, but are there more integers than there are natural numbers? Are there more rational numbers than there are integers, etc.? How do you answer these questions? Okay, so this is what we'll talk about to begin with, and then we'll talk about limits to what computers can do. So what are questions that computers cannot solve? Okay, so all right. Okay, so how we count? Okay, so this sort of goes back to the question of how do you count? And to answer these questions, mathematicians reached way back into their experience, deep into their experience, when they were in kindergarten. Yeah, and I'm sure you went through this exercise too of counting when you were in kindergarten. No counting? Okay. Well, at some point, maybe earlier than kindergarten, or maybe later, but at some point you learned how to count, and the way you learn how to count, well, hopefully, I don't know how one learns how to count, but the way you learn how to count is, I don't know, maybe you have a set of little stones or things like that, and then the way you count is you sort of make a correspondence between this and the objects that you want to count, right? So basically the counting is, so when these mathematicians reach back into the depths of their memories about how they first learned how to count, they thought, really what you teach kids in kindergarten is how to create a bijection. Okay, so what you were doing when you were in kindergarten, when you had these objects that you wanted to count, you had these 3 toys, one was shaped like that, and the other was shaped like that, and the third one was shaped like that, and you wanted to know how many toys did you have? Well, you made a 1-to-1 correspondence between that and 3 stones, and what you were doing was you had a bijection F from this set to that set. Okay, so that's okay. So it was just a matter of looking back and seeing how you got started, and so we can formalize it and we can say, remember what we said, that a function f is 1-to-1 if every element gets mapped to a distinct element. There are no collisions, right? So if f of 1 was equal to f of 2, then this would not be 1-to-1. Similarly, we say that it's onto if everything everything is hit by somebody, right? So this is an onto function because A, B, and C are all hit. Well, C is hit twice, but that doesn't matter. We don't want 1-to-1. This is just onto. And then we say F is a bijection. Sorry, F is a bijection if and only if it's both 1-to-1 and onto. Right? And so now if you want to say, well, our two sets are two sets equal? Do they have the same cardinality? Well, what we want to do is we want to create a bijection between them. Right? So we say that S and T have the same cardinality if and only if there exists a function f such that S maps to T, and f is a bijection. Right, so that's our definition of what it means for two sets to be equal in cardinality. And so, right, so now you can see that if you have any two sets which have exactly 7 elements, you can create a bijection between them, and that's why you say that they have 7 elements, because, right? But what about sets which are infinitely large? Okay. So you could ask, well, is it true that the natural numbers, well, wait, I forget, do natural numbers include 0 or do they not include 0? They include 0, right? Okay. So you have the natural numbers n, which is 0, 1, 2, ... And then you have the positive integers, which doesn't include 0. So it's 1, 2, ... Do they have the same cardinality? Yeah. And at first you might think, well, no, obviously not, because this is a bigger set than that, because it contains it. But after you think for a moment, you realize that, in fact, there's a bijection. Right? You can map every natural number to a distinct positive integer by just moving over one place. Right? Now, if you did this with a finite set, of course, you'd run out at some point, but these are infinite sets. And okay, so how do you know that it's a bijection? Right? How do you know it's a bijection? So what you have to show is that it's 1-to-1. Okay, so what is f? F of x equal to x plus 1, right? So how do you know it's 1-to-1? Well, you say, by contradiction, suppose f of x equal to f of y. Well, f of x equal to f of y means that x plus 1 equal to y plus 1, which implies x equal to y. So it's 1-to-1. If f of x is f of y, then x equal to y, so no two distinct things can collide. How about onto? How do you show it's onto? Yeah, so if you have any, if you have any number, little z belongs to z plus, then z minus 1 belongs to n, and f of z minus 1 equal to z. So it's onto. You can hit everything. So it's 1-to-1 onto, bijection. Okay, there you go. Okay. Yeah? So you have this principle that you can slide everything over by 1. Okay, now you might ask, well, what about, what if you were looking at the natural numbers versus the even natural numbers? Right, so this is 0, 1, 2, ... versus 0, 2, 4, 6, 8, ... Now, surely you might think, well, this set is surely smaller than this one. Right? And yeah, but infinity doesn't behave that way. Right? In fact, they're equally big. Okay, and that's the mapping. So you just go, okay, so it's n gets mapped to 2 times n. So you could call this 2 times n the even integers, right? And basically you're mapping f of x equal to 2x. And you can again show it's 1-to-1 onto, so it's a bijection, so there's an equal number of those. Yeah? Is everyone clear what we are trying to do? Okay. How about doing another example? How about the number of, is, n versus the number of binary strings? Finite binary strings. Okay, these are denoted by 0, 1, star. These are all elements like, well, that's a binary string, that's a binary string, that's a binary string. You can just write out any string of zeros and ones of finite length. Okay? So, any guesses? Which is bigger? First one, integer, the natural numbers are bigger. Binary strings are bigger. Same size. Oh yeah, okay, it's clear, okay. The majority is always, okay, so yeah, it's the same size. And how do you show that? So is there a bijection? Anyone? Yeah? Yeah, how about turning n into binary form? So does that give you all possible 0, 1 strings? No. Okay, so then how do you get a bijection out of it? I'm sorry?
Start with a 1-digit long string.
Yeah.
1 and 2.
Yeah.
And then add another digit, and you got 3, 4, 5, and 6.
Oh yeah, but yeah, how about just showing right, okay, so that's one way to do it, but let me show you a way of doing it in one step, right? So it's sort of, what you would do is you'd say the finite binary strings, there's a bijection between these and binary strings which start with a 1. Okay, so things like 1, 0, 1, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1. So you just put a 1 in front of everything, right? So you can see that there's a bijection between these and these. Okay? Yes? And and now you can see that there's this set, all binary strings which start with a 1. This is in 1-to-1 correspondence with the positive integers. You can't represent 0 this way, right? Because you're starting with a 1. But any other number you can represent because you just write it out in binary. Right? But then we know that there was a bijection between the positive integers and the natural numbers. So there's a bijection between this and the natural numbers. And what do you know about bijections, right? They compose, right? So you have a 1-to-1 map from here to here. It's a bijection between here and here, bijection between here and here, bijection between this and that. So for every element here, you can sort of say it maps to this one, which maps to that one, which maps to that one, right? And it pairs everything up. That's the nice thing about bijections. Yeah?
But how can we find a function that maps all of those 1, 0, 1, 1, everything to the positive integers? Do we have to show that the function that exists that would make that bijection?
Yeah, it's just writing out the number in binary. There's a unique way to take every number and write it out in binary. So that's your function. Yeah? Okay, is everyone happy with the composition of functions? So you know what I mean? So if you have a function f, which goes from here to here, So there's 1, 2, 3 objects here, 3 objects here, and you have, this is how this function f goes. And then you have a function g from here to here. So you have g such that this goes to that. These are both bijections. Then you can compose them. You can say, well, then you can map this guy to that guy, this one to that one, this one to that one. Right? You just follow the arrows. Right? So if you have a one-to-one correspondence, if you can get a bijection from here to here, then you just follow it and you get a bijection from there to there. Right? So that's why we said, if you have all these sequence of bijections, you're done, because you can go from there to there. It doesn't matter. Okay. Okay, now, here's another question we might ask. So the next question we might ask is, well, what about, let's see. Okay, so the other question we might ask is, what about the rational numbers? Okay. Well, now we are talking about something which looks very different, right? So you draw your number line, and here's, well, you know, this is your integers. You have 0, 1, 2, 3, 4, minus 1, minus 2, minus 3. And now, where are the rational numbers? They are dense, right? The rational numbers are dense in the sense that they're everywhere. You know, you make up any, you give me any two rational numbers and I can fit another one in the middle of those two, right? You give me two rational numbers, so you call this one A and that one B, then I can sort of insert a rational number in the middle, which is A plus B over 2, right? So given any two rational numbers, there's always one between them. So you can, I mean, they're completely densely packed on the number line, whereas the integers are sort of spaced out. There are infinitely many of each of them, but surely the rational numbers, there are more of them than the natural numbers, right? Shouldn't there be? No? Maybe no. More or no? No. Yeah, it's all the same. So there are just as many rational numbers as there are natural numbers, right? It's all the same. So how do you show that? Well, what you use is what's called, you know, there's a more general way of showing that two sets are equal. Rather than showing that there's a bijection, there's another way of showing it, which is what you do is, you know, you use what's called the Cantor-Bernstein theorem. So to do what? Well, so what you show is to show that cardinality of S equal to cardinality of T, the number of elements of S equal to the number of elements of T. What you show instead is you show, first you show the number of elements of S is less than or equal to the number of elements of T, and then you show the number of elements of T is less than or equal to the number of elements of S. Okay? So how do you show that one set is smaller than another? So here's the idea. So here's your set S. Here's your set T. You want to show S is smaller than or equal to T. What you do is you find a function f from S to T. Which is 1-to-1. Okay? Okay, so for every element of S, we found an element of T. And it's a distinct element of T. So we know that T must be at least as large. Because for everything here, we found something there. But it's not necessarily onto, so we don't know that this, that S is at least as large as T. Right? We know T is at least as large as S. Okay? So what the Cantor-Bernstein theorem says, okay, so it's this part, that if you can show a one-to-one map, so if you have a one-to-one function, f such that S goes to T, and a one-to-one function G such that T goes to S. So it says S less than or equal to T, T less than or equal to S. Then this implies that there exists a bijection H such that S goes to T. Okay, this is what the Cantor-Bernstein theorem says. It says if S is less than or equal to T and T is less than or equal to S, then S is equal to T. You'd imagine that this is obvious. Okay? So how did these two men get their names on something that's completely obvious? Something wrong here, right? Well, actually, it's not easy to prove this theorem. In fact, it's so non-trivial to prove this theorem that we'll just pass along and we'll assume it. Okay? So we'll assume it's true, and that's it. So, and that's how. So, okay, it makes a lot of sense, and now we're going to use it to show that the number of rational numbers is equal to the number of natural numbers. Okay. So what do we do? Well, clearly, it's easy to show that the number of natural numbers is less than or equal to the number of integers, a number of rational numbers, right? You can easily give a one-to-one function from the natural numbers to the rational. You can, right? Everyone know how to give a one-to-one function from naturals to the rationals? Actually, think about it for 20 seconds. Maybe 10 seconds. Yeah, anyone want to know the answer? Everyone know what the answer is? Yeah? Everyone? Yeah?
You want the answer?
Yeah, go ahead.
Every natural number is a rational number.
Oh, good, yeah.
Map it to itself.
Yeah, just map every natural number to itself. It's a rational number, so that's it. That's a one-to-one mapping. Now what we want to show is that the number of rational numbers is less than or equal to the number of natural numbers. So we want a function f such that the natural numbers get mapped to the rational numbers. No, sorry. What do I want? I want them other way around. Okay, sorry. So that the rational numbers get mapped to the natural numbers. So how do you do that? Okay, so remember what a rational number is? It's of the form A over B. Right? A and B are integers. Let's let it be the positive rational numbers. Okay? Just for, yeah, so it's A over B where A and B are positive integers, let's say, just for convenience. And then it'll be easy to show that the positive rational numbers there are as many of those as there are all rational numbers. You know, factor of 2 never made a difference in infinity. Okay? And then what you do is you say, well, let me actually show that all pairs of integers, you know, there are as many pairs of integers as there are integers. Okay? And this is an argument that shows it. So if you look at pairs of integers, actually, did I need positive? I guess these are positive and negative, right? So, okay, so forget that I said this. Okay, so we'll say the number of pairs of integers is as many as the number of natural numbers. Okay, how do we do this? Well, the number of pairs of integers is the number of points in the plane, right? The number of grid points in the plane. Because for every pair of integers, you can plot it as a point like this. And then to put it in one-to-one correspondence with the natural numbers, you just create the spiral. Right? And you're going to hit every ordered pair at some point. And so this shows you that the number of natural numbers is at least as large as the number of rational numbers. Okay, so we showed both directions. Natural numbers is less than or equal to rationals. Rationals is less than or equal to natural numbers. Cantor, Bernstein tell us they're equal. Yeah?
Can you explain why it's okay to repeat rational numbers? And by that I mean like the pair 1, 1 and 2, 2 and 3, 3, they're all actually representing the same number?
Yes.
So you're kind of repeating them. Why is that okay?
Well, because we said that the rational numbers the number is less than or equal to number of natural numbers. So we are saying, we are so confident about the natural numbers, we'll take you on even if you repeat yourself many times. So, you can even throw infinitely many copies of every rational number, like 1 over 1, 2 over 2, 3 over 3. It's fine, we've got it covered. Right? So, you see what I mean? So it's sort of saying the natural numbers are at least as many as the rational numbers. In fact, we'll even give you an advantage, and we'll still match you. So that's what it is. Okay, so surely at this point we can do an induction, and we can say all infinities are equal. Surely. Right? We'd be wrong. So the logician Cantor in the late 19th century discovered that, in fact, they're not all equal. That the number of real numbers is greater than the number of rational numbers. And this is a very remarkable thing. Okay, so if you want to understand why it's remarkable, let me try to give you an argument that the number of real numbers couldn't possibly be larger than the number of rational numbers. Okay, do you want to hear an argument why they couldn't possibly be larger? So we are looking at the rational numbers versus the real numbers, right? Which are there more of? Okay. And so here's an argument. Let's look at the number line again. Okay. Every point on the number line is a real number. Every point is a real number. So that's some real number R, and that's some real number R prime. Okay? And they get very dense, right? It's sort of every point is real. But then, what do we know about the rational numbers? They're dense. Right? Between any two real numbers, there's a rational number. Okay. Oh my God, what should I do? Oh, well, let's just delete it. Okay. Okay, so there's always a rational number in between them, right? So how could it possibly be, if every time you see a real number, you see a rational number after it, and right, you can, they keep interspersing themselves in the middle. How could there possibly be more real numbers than there were rational numbers? Right. So imagine you are standing in a line, and then there's this other group of people who come in, and they sort of intersperse. Every time there are two of you. These other people who are from, different part of town, maybe from Stanford. These guys are coming over, and they intersperse themselves. You're standing in a line, and between every two of you, whenever there are two Berkeley guys, they disperse themselves in the middle. How could you possibly claim that there are more people from Berkeley in the line than from Stanford? Well, maybe there could be one more, right? Because you have 10 from Berkeley, and you just need 9, but it could be only off by 1. Okay? But here, the claim is that even though you keep doing this, the rationals keep interposing themselves between every pair of reals, there are just many more reals than there are rationals. Okay? The rational numbers are countable. Every set that can be put into one-to-one correspondence with the natural numbers is called countable. The reals are uncountable. There are more of them. Okay? And what Cantor discovered is a way of proving that the number of real numbers is greater than the number of rational numbers. And it's a beautiful argument. So it's named after him. It's called Cantor's diagonalization argument. Okay. So what it says is there does not exist a function f such that the natural numbers get mapped to the real numbers where f is a bijection. There's no such bijection. Okay? So how do you prove that there's no bijection at all? Right? You want to rule out every possible bijection. So how could you possibly do that? Okay? So this was the cleverness of Cantor. It was an amazing argument. Okay? Actually, it was so amazing that he went on to prove lots of things. He was trying to prove something really remarkable. And then, so he was actually trying to show that logic itself, he was trying to put it on a consistent basis, and, he'd written his pretty remarkable set of books, and then just as he was about to publish it, I think it was Bertrand Russell, who sort of wrote to him asking him a question about his book. How do you deal with the following paradox? And Cantor realized that there was that there was a fundamental flaw with everything he had written. So he never recovered from that. Right? But okay. So but let's talk about his happier times here. And right. Okay, so okay. So here's Cantor's diagonalization argument. Okay? I hope there's one thing you'll take away from this. I hope this is one thing you'll take away from the course, that for something to be great, it doesn't have to be complicated. Right? This is one of the great arguments of the 19th century. Meaning in that entire century, this was one of the greatest arguments ever, that anybody ever came up with. And something you're going to be able to understand in a few minutes. Right? So it doesn't have to be complicated to be great. It just has to be great to be great. Okay, so here's what Cantor did. So what he said is, okay, let's assume that there's a bijection. So what does it mean there's a bijection? So I'm going to line up all the natural numbers, 0, 1, 2, 3, 4, etc., etc. And then each of these is going to be mapped to a real number. Okay, so let's write it out. 0 gets mapped to that one, 0.52, 1, whatever it is. 1 gets mapped to, 2 gets mapped to, 3 gets mapped to, and so on. So what's a real number? In fact, let's just only work with the real numbers between 0 and 1. So it's 0 point something, something, something. And we'll show that there isn't a bijection here. That there are more real numbers between 0 and 1 than there are natural numbers. Okay. So, and then, since it's called his diagonalization argument, Cantor decided to look at the diagonal. Okay. So you look at the diagonal down there, and then what do you do to it? Let's sort of disrupt the diagonal. Okay, so let's do something to it. Let's take every digit on the diagonal and let's replace it by something else. So let's map 5 to, I don't know, 8. Let's just do this thing where we are just taking this, here's a table that somebody made up, and all we want to do is we look at the diagonal and we disrupt it. Okay, so maybe we mapped 5 to 8, we mapped 4 to, okay, let's do it in a systematic way. We'll just add 3 mod 10, right? So 7 goes to 0. 0, yeah? 9 goes to 2. Okay, so we just do that. And now, let's look at a real number. So let's look at a real number, 0.8702 ... Okay, you see how I got this 0.8702? It's the disruption of the diagonal. Okay? And now, we are going to scan down this list, and we are going to see where along this list did this number occur. It's a real number. Where did it occur along this list? Okay. Well, so maybe it occurred here, right? This was exactly where this number occurred. Okay. Well, could it actually happen? Well, no, because you just look at the diagonal and you look at that digit, and they don't match up. Yeah? So he put his destructive tendencies to really good use here. Yes. I'm sorry? What if they end earlier? Then you just write 0, 0, 0, right? If it's a real number, it ends earlier, then you just put 0, 0, 0, and then you, yeah? Okay. Maybe there's a related question. So let's talk about a related question. So what if instead of real numbers, these were rational numbers? So you know how a rational number goes? You can also write it rational numbers between 0 and 1. You can also write it as a decimal expansion. And some of them will end early, and then you'll just get 0, 0, 0. And others, what does a decimal expansion of a rational number look like? Well, eventually it cycles, right? It keeps cycling. Yes? Okay, but you can still write a decimal expansion for the rational numbers. So now, what if we try to use Cantor's argument to show that you couldn't have a bijection from the natural numbers to the rational numbers? Yeah? Well, we shouldn't be able to do that because we already said, that there's a bijection, right? There's an equal number of them, there's a bijection. But let's see what would go wrong, right? So to understand whether we really figured out all the subtleties of this argument, let's go through the argument and see what goes wrong. Okay, so we start by saying, okay, let's assume that there's a bijection from the natural numbers to the rational numbers. Okay, so here's one of them. Okay, and the only difference is that these numbers that I wrote up there, they are eventually periodic. Okay, so then we go ahead and create the diagonal. We do the same thing. We disrupt the diagonal, and then we write it out, and we say, here's a number that couldn't possibly be anywhere on the list. So we are done. There's no bijection between the rational numbers and the natural numbers. What went wrong? Something must have gone wrong, right? Because it was too easy. Yeah. Give it a minute. Give people a minute. A question, or do you know what the answer is? Yeah. Okay, so shall we talk about what went wrong? So the first point, there was nothing wrong with the first assumption that there's a bijection. So we are assuming for contradiction there's a bijection. So we did this. There was nothing wrong with creating the diagonal set. We have every right to look at the diagonal. There was nothing wrong with disrupting the diagonal. That's just our right to do that. There's nothing wrong with writing that number down here. There's a free country. There's nothing wrong with asking whether this number occurred anywhere on the list. We can ask the question. There's nothing wrong with concluding that that number couldn't have appeared on the list because of the diagonal. Yeah?
Could you go over why we know the disrupted number is not in the list?
Oh, yeah, okay, so let's go over that again. So why is this number not in the list? Because we say, okay, let's suppose it was in the list out here. Okay? Now, look at that diagonal entry. The number on the list had some diagonal entry. What about this number? It had the disrupted entry. So they don't match up. Yeah? Okay. Yes?
So we're saying that this line we're saying that number was on or is currently on?
We are just trying to say, did this number exist in the list? After the disruption.
So we're saying that it was there before the disruption.
Well,
We're assuming it was in this line before the disruption, and it can't be in there anymore because we disrupted it.
no. We are saying we are looking at this number, which we created, the number along the diagonal, right? And we are saying, where did this number occur in the list? Right? Here's a number. Where did it occur in the list? Right? We don't see it anywhere. Right? Could it occur? And here's a missing number. Yeah.
But it couldn't have been in a different spot with a similar series of numbers. So after the disruption, make it that number?
No, you see, the list is, the list goes from top to bottom. Now, this number we are asking, does it occur anywhere in the list? Anywhere meaning it's an item in the list. It's the first number, the first row, second row, third row, etc. Right? So suppose we say it was the 17th row of the list. This is the number, 0.8702, etc., etc., etc. So then we are going to say, well, look at the 17th digit, because it was the 17th number. That's this diagonal digit. Well, the number in the 17th number, this digit was say 3, but we disrupted it, and the corresponding digit here is 6. These two don't match up. They are not the same number. So sorry, you tried to mislead me by saying that this number occurred here, right? And we are claiming no matter where you try to point me to, I'll show you that there's one digit where it really doesn't match up, and so it couldn't be the same number. Yes?
Is there any guarantee that this number can be rational?
Yeah, okay. So we finally get to the point. So we are saying, so far everything was correct with the argument. We said, this number can't possibly exist on the list. But we are trying, but so what? You showed me that there's a number that's not on the list. I don't care. If you want a contradiction, you have to show me that there's a rational number that didn't exist in the list. And we have no guarantee that this number is rational. Because for it to be rational, it has to be eventually periodic. And there's no reason it should be eventually periodic. The reason the argument worked in the real number case is because we said a real number is any decimal expansion. Right? You create any decimal expansion, that's a real number. Right? You put down 0.8702 ... You're free to fill in the dots any way you want. That's that's up to you. That creates a real number. So that's what we did. We looked at the diagonal. It's a filling in of the digits in some way. And whatever that filling in was, this must be a real number. And so since it was a bijection, this was supposed to be a bijection, this real number should have occurred somewhere. It should be somewhere on the list. But we showed that it can't be anywhere on the list. And that's how we got the contradiction. Yeah? Yes?
I have a question. So, okay, let's say you had the argument that you have the decimal 0.1.
Yeah.
And you say that maps to 1.
Yeah.
Then 0.11 maps to 2. You could argue that you could always add like another digit to the right, and then it will infinitely grow, and those are all real numbers, right? So you can say that just that case will take infinite numbers to cover, so then you'll never reach like other numbers.
No, but see, we could have done that with the integers versus the natural numbers. We could have said, well, you couldn't possibly have a bijection between the integers and the natural numbers because look, the integer 0 corresponds to 0, 1 corresponds to 1, 2 corresponds to 2, and so on. You're using up everything. But now when you have nothing left over to cover -1, -2, and so on. But we saw you can make a bijection between, did we see? We didn't see. You can make a bijection between the natural numbers and the integers. How would you do it? Well, you would say, well, there's a bijection between the natural numbers and the even natural numbers. There's also a bijection between the natural numbers and the odd natural numbers. We saw a bijection between natural numbers and the evens. There's also one between the odds. So you could take the integers and break them into two parts. There's one side of the line, there's the other side of the line. You match up one with the evens, one with the odds. You've covered everything. Right? So the problem here is, when you're dealing with infinity, it's up to you how you do the bijection. And you can't just say, well, this particular bijection didn't work, therefore I conclude. No, you've got to show no bijection could possibly work, no matter how clever. Right? And this is what was so remarkable about Cantor. He said, no bijection will work. You try to be as clever as possible, you make up that bijection, I'll show you something that doesn't work. Okay. Okay. So, yes?
Anytime you're trying to prove this, is it always necessary to prove it using the last number in the list?
I'm sorry?
Like, I understand that the list is going to be infinite, but, yeah.
Yeah.
And that contradicted the fact that it could be in the list.
Yeah.
But is it necessary to show, like assume that that's the last element in the list?
No, it's not. It's not the last in the list. I just said, this list goes on till infinity. It's an infinitely long list because the list is a list of all natural numbers. So there are infinitely many elements in the list. This was just some row in the list. The list keeps going on. Yeah? Okay. Okay, so let me talk about now a related idea, which is something very, very fundamental to computer science, which is, there's a sequence of questions like, for example, is there, so for example, maybe you're worried that about, that your computer might get infected with a virus. And so you'd like to create a perfect test to tell whether something is a virus. Okay. Could you possibly do that? Right? Okay, so there are a number of questions like this. Or let's say that you wrote a program and you want to know for sure that it'll never loop. It'll never go into an infinite loop. Right? It'll always halt. Okay? So, there are things that you would want to put into your compiler or into your tester. Things where you test that an unknown program has a certain property. Okay? It turns out that one of the earliest things we learned about computers was that there's no way to test these things. That there are things that computers cannot do. Okay. Do you know how early in the history of computers this was learned? It was learned before the first computer was built. In fact, it was the proof that there were limits to what a computer could do, which led to the first conception of a computer. Okay, so this was in the work of Alan Turing, a logician. Okay, he actually came up with this idea about what a computer could not do. And that was where he formalized, he wanted to formalize the notion that there are certain things you could not do algorithmically. And to formalize this notion, he came up with this notion of a Turing machine. Okay? And that was sort of the first formal model of a computer. So let's try to understand Turing's argument. Okay? Again, like this other argument, like Cantor's argument, it's a very simple argument. Okay, it's a very simple and beautiful argument. And again, Cantor's argument was one of the greatest arguments in the 19th century. Turing's was one of the greatest from the 20th century. And both of these are very, very simple arguments, right? They're so simple you can fit both of them into one lecture. Yeah, okay, so what is this, what is Turing's argument based on? It's based on something called the liar paradox. Okay, so it goes like this. So suppose you have a statement like this. This statement is false. Now you're trying to determine what's the truth value of this statement. Is it true or false? Okay. And you think about it for a moment and you say, well, maybe it's true. If it's true, then what it's asserting is true, then it must be false. But then maybe it's false. But if it's false, then what it's saying is it's false, so it must be true. Right? So you get into this, it's a complete disaster. It can't be true, it can't be false. Okay, so this was, this kind of statement had been around for a long time. It was discussed by the in some related form by the ancient Greeks. It was discussed by, by various other civilizations, in different forms. It was always seen as some sort of paradox or some sort of recreational math and so on. And it took Turing to really extract the essence of it, and show that this was a very powerful kind of paradox, something that you could use to understand something very, very basic about computation, about what you could compute. And then in the process of formalizing it, actually formalize the notion of a computation on a computer. Okay, so how do you make use of it? So let's first realize the following. So what we want to know is there can you write a program? Is there a program that takes as input another program, right? Takes as input a program P and tells whether it halts on a given input. Does program, okay, so this is what you're trying to answer. Does program P halt on input I? Okay, that's what you're trying to answer. And one of the first things you learn in computer science, maybe you learned this in 61A, is that there's some sort of equivalence between program and data, right? You can view a program as a bit string, and there's no reason you shouldn't think of it as data, right? You can give a program as input to another program. That's what a virus is too, right? It's a program which is an input to another program. Okay, so what we are really interested in is a program like this, test halt, right? It takes as input a program P and an input I, and it should output yes if the program P halts on input I, no if program P loops on input I, if it never halts, right? So we want to know, can you possibly write such a program? Okay, and what Turing answered is that there's no way of writing such a program. This does not exist. Okay, so what Turing said is test halt does not exist. Okay, so how did he do this? So here's what he did. He wrote this program called Turing. That's cut off there. It should actually say, let's see, is that better? Turing. No, maybe. Okay, let's try again. Okay, is that better? Well, at least it's less readable, so you can imagine that it says Turing. Okay, so that's a program says it's Turing on input P. It says, okay, so you can feed the program P input P, right? So it sort of asks this question. It says, if you took the program P and you fed it as input its own description, would it halt or would it not halt? Okay. There's something sort of vaguely disturbing about this, but these are programs. You can feed them to themselves, and it's all okay. So this is the question Turing was asking. Does P halt on its own description? And then he said, let's do something perverse. What Turing is going to do is, if P halts on its own description, then Turing is going to loop forever. And otherwise, it's going to halt. Okay? So if test halt was a well-defined program, then Turing is a well-defined program. It takes as input only a program. Remember, programs, inputs, strings, they are the same thing. So it takes as input a program, and then it asks test halt, does this program halt when you run it on when you give it as input, its own description. And if it halts, then it says, just go into an infinite loop. Just keep doing the same thing over and over again. If test halt tells you, no, this program doesn't halt on its own description, then halt. Okay? Now, Turing is a program, right? So you can ask, what does Turing do on input Turing? Well, so what would it do? On input Turing, it would say, it would call test halt on input Turing. Right? It would ask whether Turing halts on input Turing. And if it halts, then it would say, then it says, go ahead and loop forever. And if it loops, it would say halt. So now, what does Turing do on input Turing? Right? So if it halts, it loops. If it loops, it halts. It's like the liar paradox. So we have a contradiction unless something happens, right? So we started with an assumption. So our assumption was there was this program test halt. And so that's what has to break. So you can say, as a result, there cannot be any such program. So there's no test for halting. You can try to test for halting, and you can, maybe it'll work sometimes, but you cannot write a program that guarantees that it'll tell you whether a given program halts or loops. It's just impossible. Okay? Yeah.
If you say that you have a test program that can test if the program halts or loops on any input other than itself.
Well, but how does it tell? How does it tell whether it's itself? So test halt is just taking two, a program and an input.
Wait, you can say like it would work for any other.
Other than. So test halt didn't know about Turing, right? It's just a program that can test for halting. Right? It takes as input a program, the description of a program, and a description of an input. And you tell it, well, tell me whether this program halts on this input. That's all it is. Right? And we just called it as a subroutine inside another program. And that's where the problem comes up. So, the moral of all this is that programs are extremely powerful objects. It's very hard to reason about them. And the reason it's hard to reason about them is because of self-reference. Right? They can refer to themselves. And that's very difficult to deal with. Right? Here's another way to think about it. What Turing's argument is a diagonalization argument. Okay, so why is it a diagonalization argument? Okay, so what you do is you can enumerate all possible programs. Okay? And you can enumerate all possible inputs. Okay? And what you can do is, what it's doing is it's saying, well, here's a program which looks at the diagonal of this, and it flips it. You know, wherever this said halt, it loops. Wherever it said loop, it halts. Okay? Now, this is a new program. You know? And where does it fit in this as a row? And the claim is it can't fit anywhere. So it just can't, so you're diagonalizing. It's the same argument all over again. Yeah? So this was Turing's diagonalization argument. So building on Cantor. Okay? Okay, so if you want to learn more about this, this is covered in much greater detail in CS172, which talks about models of computing, things like that. So you can learn there that almost every property you want to know about programs is uncomputable. Okay. Now, so let me just wrap up by saying a little bit about this class. I hope it wasn't too, you learned a lot from it. But so here are a few things I hope you learned. There was of course this stuff, which is totally relevant to things like computability and models of computation, CS172. There's what you learned about modular arithmetic, which applies to your course in security, like 161. Actually, it also shows up in 191, the quantum computing course. It, then we talked about, the early stuff, induction, sort of propositions, etc., logic, which shows up in your AI course. Induction, of course, shows up everywhere. I don't even know where all. It, of course, shows up in your algorithms course and so on. We did a little bit of graphs, and then we talked about polynomials, error-correcting codes, which if you're doing electrical engineering, and this is sort of bread and butter in information theory. And finally, there was probability theory, which, as you saw, is extremely, it's sort of, it cuts across the field in terms of inference, in terms of AI, in terms of many parts of the department. So, but this course was hopefully not just a sum of its parts. It was ideally at some point, ideally you got something out of it already, or if not, then hopefully you will get something out of it, which is this notion that, it's not always the case that great and deep things are complicated. Often it's the simplest ideas that are the most powerful ones. The other thing is that when you're faced with a problem that you're trying to solve, it might seem complicated, right? That's how it seems to us often. And sometimes there's nothing to it except, you have to sort of fight your way through the thicket and, with a machete, and, that's the only way through. But in this course, at least, hopefully it showed you how to do, or hopefully, if you haven't yet, maybe you will figure it out, that there are these questions where you can find an easy path through. And, this happens, in this course, it was designed to make it easy to find those paths because you knew there was one, and, it's that kind of material. But hopefully, if you learn this, if you learn this this kind of skill, then you can actually use it later where it's not so clear whether there's an easy path through, but often there is, and it's a really, it's one of the important skills to have. Of course, it's also important to have a big machete, so if you're faced with an undergrowth, you can sort of whack your way through it, but sometimes it's better to find this path.